All right. So, in 3.1, we discussed the solutions of linear systems without worrying about how we came up with the actual solutions. We used the guess and test method. Um, in this section, we used the geometry of the vector field to find special solutions of linear systems. We begin by reconsidering an example from the previous section. The direction field for the linear system dy dt is equal to a times y, where a is this matrix. Looking at the direction field, we can see there are two special lines through the origin. The first is the x-axis, on which the vectors in the direction field all point away from the origin. The other special line runs from the second quadrant to the fourth quadrant. Along this line, the vectors of the direction field all point directly toward the origin. Because solution curves for the system are always tangent to the direction field, a solution that has its initial condition on the positive x-axis moves to the right, directly away from the origin. A solution with the initial condition on the negative x-axis moves to the left, directly away from the origin. Similarly, a solution with the initial condition in the second quadrant on the special line moves directly toward the origin. There are solutions to this system that lie on straight lines through the origin in the phase plane. In section 3.1, we saw that there are two solutions that are linearly independent for this system. Now let's consider the geometry of these two solutions in the phase plane. To plot the solution curve for y1 of t, note that the x-coordinate thus the solution curve lies on the positive x-axis. Moreover, y1 of t goes to infinity as t goes to infinity and tends to the origin. Y1 of t tends to the origin as t goes to minus infinity. So y1 of t is a solution that tends directly away. Okay. For y2, it's convenient to factor out the e. This representation tells us that as t varies, y2 of t is always a positive scalar multiple of the vector minus 1, 2. Since positive scalar multiples of a fixed vector always lie on the same ray from the origin, we can see that y2 of t parameterizes the ray from 0, 0 with slope minus 2 in the second quadrant. Okay, and it approaches the origin. We can see that the formulas confirm what we guessed by looking at the direction field. There are solutions of the system that lie on two distinguished straight lines in the plane. Straight line solutions are the simplest solutions for systems of differential equations. As those solutions move in the xy plane along straight lines, it is important to remember that the speed at which they move depends on their position on the line. In this example, solutions go to 0, 0 or escape to infinity at an exponential rate. Assuming that the system has straight line solutions, not all linear systems do, we turn our attention to finding formulas for them. The basic geometric observation is that a straight line solution through the origin, that along a straight line, the vector field must point either directly toward or directly away from 0, 0. That is, if v is equal to xy is on a straight line solution, then the vector field at xy must point either in the same direction or in exactly the opposite direction as the vector from 0, 0 to xy. We now turn our observation into an equation that we can solve to find straight line solutions. For a linear system, the vector field at v is the product of is the product AV of A times V. Hence, we seek vectors x or y equal to xy, v equal to xy, such that AV points in the same or opposite direction as the vector from 0, 0 to xy. That's right. So this is the so that there's a scalar multiple of some point such that the transformation of the product of A times V is equal to some scalar multiple of V. If lambda is greater than 0, then the vector field points in the same direction as xy, away from 0, 0, and otherwise towards 0, 0. This equation can be written more economically as AV is equal to lambda V. And it is important to remember that this equation is the key equation for finding straight line solutions of the linear system dy dt is equal to A times y. Okay, so then we do this math. Then we do this. And then we solve. There's one obvious solution to this system of equation, namely the trivial solution. We already know that the origin is an equilibrium solution. So this solution definitely does not give us a straight line solution. We need a non-zero solution of what we need is a non-zero solution of this system of equations. To find a non-zero solution, it is important to notice that the simultaneous equations really have three unknowns, x, y, and lambda. In fact, we need to determine lambda before we can solve for x and y. If we write the simultaneous equations in matrix form, we have this. Now recall that we can use the determinant to see if such a system of equations has non-trivial solutions. These equations have non-trivial solutions if and only if the determinant is 0. Therefore, by computing the determinant, we find that this system has non-trivial solutions if and only if the determinant is equal to 0. So they just expand this out. This calculation tells us that we will have non-trivial solutions to our equations only if lambda is equal to 2 or minus 4. All other values of lambda do not yield straight line solutions. Incidentally, recall that our two straight line solutions involve exponentials of the form e to the 2t and e to the minus 4t. In a moment, we will see that the appearance of lambda equal to 2 and lambda equal to minus 4 in the exponents is no accident. If lambda is equal to minus 4, then the simultaneous system of equations becomes simply 6x plus 3y is equal to 0. So we find that y is equal to minus 2x. There's an entire line of vectors that satisfy these equations, and one possible choice is xy is equal to minus 1, 2. Note that minus 1, 2 is exactly the initial condition for the straight line solution. Okay. If lambda is equal to 2, then these become the equations. Both equations are satisfied as y equals 0. Thus, any vector of the form x comma 0 with x not equal to 0 gives a non-trivial straight line solution. That is, anywhere along the x-axis, the vector field points directly away from 0, 0. One vector along this line is 1, 0, which is the initial condition for the other straight line solution. All right, eigenvalues and eigenvectors. The cool way to describe this. What's up? All right. We will return to this example in a moment, but we first generalize these computations so that we can apply them to any linear system. Consider the general linear system, y prime is equal to a times y. To find straight line solutions through the origin, we must find non-zero vectors v such that the vector field at v points in the same direction or directly opposite to v. So we seek non-zero vectors such that av is equal to lambda v. Given a matrix A, a number lambda is called an eigenvalue of A if there exists a non-zero vector v equal to xy for which A times v is equal to lambda v. The vector v is called an eigenvector corresponding to the eigenvalue lambda. The word eigen is German for own or self. An eigenvector is a vector where the vector field points in the same or opposite direction as the vector itself. Okay, so here's an example. The vector 6 minus 2 is an eigenvector with eigenvalue 3 because we multiply A times the eigenvector, and then we multiply 3 times V, and we find that they're equal. Also, the vector minus 1, 1 is an eigenvector with eigenvalue 1. It is important to remember that being an eigenvector is a special property. For a typical matrix, most vectors are not eigenvectors. And 17 minus 2 is not a multiple of 2, 3. All right, lines of eigenvectors. Given a matrix A, if V is an eigenvector for eigenvalue lambda, then any scalar multiple K times V is also an eigenvector. To verify this, okay, you do A times KV is equal to this just by the definition of matrix vector multiplication, and then, or the linearity of it. Then we know that this is equal to this, so then, and then scalar multiplication is commutative. Actually, that's interesting. I guess for vector fields, we always require fields don't have to be commutative, right? Anyways, I don't think so, but that would be really weird to think about that in terms of a non-commutative field. All right. Where the first equality is a property of the matrix multiplication, the second equality is the fact that V is an eigenvector. Hence, an eigenvector V and... Okay. Computing eigenvalues. To find straight line solutions of linear systems, we must find the eigenvalues and eigenvectors of the corresponding coefficient matrix. We need to find the vectors V such that AV is equal to lambda V. Okay, so for a general matrix ABCD, we have ABCD times XY is equal to lambda XY. Okay, so then we can subtract off the lambda Y from this side, and then we can compute the determinant to find this. Okay, we encounter this matrix each time we compute the eigenvalues and eigenvectors. We introduce some notation for it. The identity matrix is the ones on the diagonal. This matrix is called the identity matrix because I times V for any V is equal to V. Also, lambda I represents the matrix. Yep. Okay, computing the difference between the matrices A and lambda I by subtracting the corresponding entries yields. Great. Thus, our determinant condition for a non-trivial solution is the determinant of A minus lambda I. So what you need to remember is the equation form of that. Because the equation form, I feel like, is the most illustrative. All right, the characteristic polynomial. To find the eigenvalues in the matrix, we must find the values for which the determinant of the A minus lambda I is equal to 0. If we write this equation in terms of the entries of A, we find that, which expands to the quadratic polynomial, that this polynomial is called the characteristic polynomial of the system. Its roots are the eigenvalues of the matrix A. The quadratic polynomial always has two roots, but these roots need not be real numbers, nor must they be distinct. If the roots of the characteristic polynomial are not real, we say that the matrix A has complex eigenvalues. We will study the behavior of complex eigenvalues in 3.4. In the case of a single root of multiplicity 2 is in 3.5. All right, consider our classic example that we've been going through. This matrix has the characteristic polynomial lambda squared plus 2 lambda minus 8, which has roots lambda 1 equal to 2 and lambda 2 equal to minus 4. As we saw earlier, these numbers are the eigenvalues of this matrix. This example is somewhat unusual in that it is not necessary to expand . the expression determinant of A minus lambda I is equal to... Okay. Oh, yeah, because it's lower triangular or upper triangular or whatever. Because this 0, then the determinant makes it so that you just have the diagonals or the eigenvalues. All right, computation of eigenvectors. The next step in the process of finding straight line solutions of a system of differential equations is to find the eigenvectors associated with the eigenvalues. Suppose we are given A, and we know that lambda is an eigenvalue. To find the corresponding eigenvector, we must solve the equation AV is equal to lambda V for the vector V. If we write V is equal to XY, then AV equals lambda V becomes a simultaneous system of linear equations in two unknowns, X and Y. In fact, the equations are just like we had before, except we now know lambda, right? Right, so before we were finding the values, we were finding basically the values of lambda such that we know that there are non-trivial solutions. And we need a non-trivial solution okay, in order to find actually a line that satisfies the equation. Okay, so now, since lambda is an eigenvalue, we know that there's at least an entire line of eigenvectors that satisfy the system of equations. This infinite number of eigenvectors means that the equations are redundant. That is, either the two equations are equivalent or one of the equations is always satisfied. For example, suppose we are given 2, 2, 1, 3 as our matrix. We find the eigenvalues of B by finding the roots of the characteristic polynomial. The roots of this are 4 and 1. So 1 and 4 are the eigenvalues of B. To find an eigenvector for lambda 1 is equal to 4, we must solve B times x1, y1 is equal to the matrix times x1, y1 is equal to 4 times... Okay, so then we get this system of equations. Now we subtract the right side and note that these equations are redundant. Oh yeah. Multiply both sides of the second by minus 2 to get the first. So any vector x1, y1 that satisfies the second equation is an eigenvector. This equation specifies the line y1 equals x1 in the plane. Any non-zero vector on this line is an eigenvector of B corresponding to the eigenvalue lambda 1 equal to 4. Okay, for example, 1, 1 and minus pi are two of the infinitely many vectors for B corresponding to the eigenvalue lambda 1 equals 4. For the other one, we do the exact same process. Here, notice that they're not... Wait. Oh. Okay, so these equations are redundant. So the eigenvectors corresponding to this eigenvalue are on this line. y2 is equal to minus x2 over 2. All right, straight line solutions. After all of the algebra, the last few, it's time to return to the study of differential equations. Just to summarize what we have accomplished so far, suppose we are given a linear system of differential equations. To find straight line solutions, we first find the eigenvalues of A and then their associated eigenvectors. Once we have this information, we have determined the straight line solutions. To do this, suppose that lambda is an eigenvalue with the associated eigenvector v. Then consider the function e to the lambda t v. For each t, y of t is a scalar multiple of our eigenvector. So the curve given by y of t lies on the ray from the origin through xy. Right, because this is a scalar, so it has to stay on the line. It's collinear. Okay, so moreover, y of t is a solution of the differential equation. We can check this assertion by substituting y of t in the differential equation. Okay, so that just checks that it's a solution. Yeah. So we're taking d dt of this vector, which is going to be lambda e to the lambda tx. Okay. On the other hand, we have a y of t is equal to a e to the lambda t. Okay, so this is the left-hand side. This is the right-hand side. Okay, yeah, cool. Since v is an eigenvector of a, yeah, but you need the fact that av is equal to lambda v. Otherwise, this doesn't work. All right, comparing the results of these two computations, we see that dy dt is equal to ay is equal to ay. So indeed, y of t is a solution. This is an important observation. We've obtained formulas for straight line solutions using just the eigenvalues and eigenvectors. Sometimes we can do even better. Suppose we find two real distinct eigenvalues, lambda 1 and lambda 2 for the system of eigenvectors v1 and v2 respectively. Since v1 and v2 are eigenvectors for different eigenvalues, they must be linearly independent. Wait. This line, I don't quite see. Any scalar multiple of v1 is an eigenvector, so consequently it does not lie on the line through the origin determined by v1, and v1 and v2 are linearly independent. Thus, the two solutions are linearly independent. Therefore, by using the linearity principle, the general solution of the system is right. Okay. Oh, okay, that's pretty cool. Yeah, that makes sense. All right. So yes. So they're independent because you assume they're not, and you show that the only way to do that is by setting the the parameters, the coefficients to 0, corresponding to only the trivial solution. Okay. So then you get the general solution. So suppose the matrix A has real eigenvalue lambda with associated eigenvector v. Then the linear system has the straight line solution e to the lambda t times v. Moreover, if lambda 1 and lambda 2 are distinct real eigenvalues with eigenvectors v1 and v2 respectively, then the solutions are linearly independent, and this is the general solution. This is a powerful theorem. It lets us find solutions of linear systems of differential equations using only algebra. All we need to do is find an eigenvalue and an associated eigenvector. There are no tedious or impossible integrations to perform. One caveat here is that the eigenvalue must be real. The theorem also explicitly provides the general solution of certain linear systems, namely those that have two distinct real eigenvalues. We will treat the possibility that the eigenvalues of A are real but not distinct in 3.5. All right, putting everything together, let's combine the geometry of the direction field with the algebra of this section to produce the general solution of a linear system of differential equations. Okay, consider 2213 like we had before. The direction field for the system is depicted in 3. Okay. There appear to be two distinguished lines of eigenvectors, one cutting diagonally and the other one the other way. The associated eigenvalues are positive since the direction field points away from the origin. Okay, so then they find the eigenvalues and the eigenvectors and they produce the general solution. For v1, we can use any eigenvector associated with the eigenvalue lambda 1 equals 4, and similarly for lambda 2. All right, harmonic oscillator. Consider the harmonic oscillator with mass 1, spring constant 10, and damping coefficient 7. Okay, so then we get this system, and then we can solve it, and they find characteristic polynomial, then they find the eigenvalues, then they get the eigenvectors. If these two equations are redundant, if they're not redundant, a mistake was made. Okay, set y1 equal to 1, and you get the eigenvector. Similarly, we compute the eigenvector for lambda 2 equal to minus 2 is 1 minus 2. Do you notice anything special about these? Let's see. One minus 2 and 1 minus 5. Using this formula, we can find the exact position of the oscillator at any time. Moreover, you can also determine qualitative features of the model from these formulas. Each term in the expression for y contains an exponential of the form where lambda is less than 0. Consequently, each term tends to 0 as t increases. Notice this is consistent with the directions of the solution curves in the phase portrait, but it is comforting to see that everything fits together so nicely since the general solution... Okay, so remember that for me, I'm going to have a hard time remembering that the general solution of these harmonic, higher order things where you converted to first order it's still a scalar solution. So you need to remember to just take the first component. One thing that we learned from the eigenvalues that we did not know from the phase portrait alone is the fact that every solution tends to 0 at a rate that is at least comparable to the rate at which t or e to the minus 2t tends to 0. All right. Let's get some practice. I kind of want to do this on the board. Yes, we're doing differential equations, and I will be back in 1 minute. But you can read through some of the problems. We're probably going to do the odd problems. Maybe I'll just do it on paper. I think paper might be the best. Okay, 3.2 straight line solutions. We're going to be trying to get through 4 sections today. I usually try to get through 3, but I have a lot to do. Okay. All right. Problem 1. Okay, so let's do this, 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 and finally this. All right. So A is find eigenvalues. Okay, so the way we find the eigenvalues, remember, is that I'm just going to do the derivation again and again so that it just hammers home. But so what we're going to have is we're going to have A, so this is A, this matrix. So then we're going to have A times Y is going to be equal to lambda times Y. Or alternatively, we could say that V is equal to XY, but it's some vector, and then AV is equal to lambda V. Okay, so then what we can do is we can actually rewrite this as lambda times I times V, which is going to be equal to something like lambda 0, 0 times V. So then we can subtract this from both sides, and we're going to get AV minus lambda IV is equal to 0. But by the fact that these are both matrices, we could actually do A minus lambda I times V is equal to 0. Okay? So then once we have that, we can actually turn this into, 3 minus lambda times 2, or 2, 0, minus 2 minus lambda. Okay, notice that this is actually going to be, that this is upper triangular and this is a 0, so that the det of this, so what we're going to try to do is find places where the determinant is equal to 0. And the reason for that is then we can find non-trivial vectors such that AV is equal to lambda V. Okay, nice. So what we're going to find is, since it's upper triangular, the eigenvalues, the eigenvals are 3 and minus 2. So lambda 1 equals 3, lambda 2 equals minus 2. Okay, so now for part B, we're going to find the eigenvex. So the way that we're going to do this is, and I'm going to do it like this. We're going to have 3x plus 2y is equal to 3, wait, let me, hold on. So we're going to have ax is equal to lambda x, or let's make it v for consistency. It's v. So for the first equation, we're going to get, 3x plus 2y, and then we're going to get 0x minus 2y is equal to, and then this is going to be lambda v on the right side. So this is going to be 3x, and this is going to be 3y. So then we're going to get, we're going to get 2y is equal to 0, and minus 5y is equal to 0. So y is equal to 0. So then x can be anything, though, right? Because x could be, pi, and it doesn't matter because it's 0 here and it's equivalent here. So then x is free. So so we could take the eigenvector to be, so the eigenvec corresponding to lambda equal to 3 is, for example, like 1, 0. So then for any, k times 1, 0 is going to be an eigenvector. So now we're going to do the second one. We're going to get 3x plus 2y is equal to minus 2x, and then what is it? 0x minus 2y is equal to minus 2y. So then we're going to get 5x plus 2y is equal to 0, and 0 plus 0 is equal to 0. So since this second equation is totally null, we can say that we're going to get y is equal to minus 5/2 x. So if we take x to be 1, then y is equal to minus 5/2. So then we have this line, 1 minus 5 over 2. That's going to look like, so we're going to have this line, make it bold or something, is an and then we're going to have 1 minus 5. So we're going to have like this. And this is for lambda equal to minus 2. So this is going to be pointing inward, and this is pointing outward. So that's the picture. Okay, so let's just check. So, okay, so did we do everything? We found the eigenvectors. It said sketch the direction field. So what I'm guessing is that you're probably going to get something like this. We're going to get something like this. You're going to get something like this. And you're going to get something like this. Okay, and then for each eigenvalue, specify a corresponding straight line solution. Well, we could just pick, 1 minus 5/2, right? And then we can pick, so this is for D, and we can pick 1, 0. So those are initial conditions for this. Okay, and plot its x of t and y of t graphs. Okay. Okay, so what we're going to have for D, just make sure that I'm in frame here. Okay, so we're going to have 1, 0, and the plot is going to look like this. Y stays constant, so this is y of t. And then x is just going to go like this. Okay, then for 1 minus 5 halves, we're going to have x go like this, and y is going to go like this. So this is y of t, and this is x of t. All right. Now E, the general solution is K1 times E to the minus, or E to the, what were the eigenvalues? I think it was 3. Yeah. E to the 3t times 1, 0. But is that right? Is that what we're supposed to do? Yeah. Plus, so this is y of t is equal to, or v of, no, big y of t. That's what it is. Okay. Plus k2 e to the minus 2t times 1 minus 5 halves. All right, cool. So now let's just jump over to the next problem, which is 3. We're not going to do 2. We could do 2, but let's just do the odds. All right, so y prime is equal to ay, where a is equal to minus 5, minus 2, minus 1, minus 4. All right, so we need to find the eigenvalues. So we're going to make that, and I'm just going to do a few of these just to like hammer it in, you know. All right, so we're going to get minus 5 minus lambda times minus 4 minus lambda. So, okay, wait, let's just do the equation again. So we're going to try to find v such that a times v, which is equal to the vector field at some position v, is a scalar multiple of v. So then if we turn this into AV is equal to lambda times the identity matrix times v, which is going to be the same because IV is equal to v. So I'll just write that IV equals v for all v. So then we're good there. Then we can do this. AV minus lambda IV is equal to 0 is equal to A minus lambda I V is equal to 0. So we're just going to keep re-deriving this just so that we remember it. So we're going to get, so then the only way this has non-trivial solutions is if det of A minus lambda I is equal to 0. So that's what we're doing here, is we're computing the determinant. So we're getting A minus so if this is like A, B, C, D, we're going to get A minus lambda times D minus lambda minus B, C. So we're going to get this, and then it's going to be minus 1 times minus 2. So then it's just going to be, let's see, 20 plus 5 lambda plus 4 lambda plus lambda squared minus 2. So we're going to get lambda squared is equal to plus 9 lambda plus 18 is equal to 0. So then lambda is equal to 6 and 3. So just to be clear, lambda 1 equals 6, lambda 2 equals 3. It's a convention, but it's more so just to remember which is which, because you can mix them up. Okay, so now what we can do is we can actually plug in this equation for lambda. So we're going to get A times V is equal to 6V, which is equal to minus 5, minus 2, minus 1, minus 4 times x and y is equal to 6x, 6y. There it goes. So now we can just turn this into an equation. We can get minus 5x minus 2y is equal to 6x. And then minus x minus 4y is equal to 6y. So this becomes minus 11x minus 2y is equal to 0. And minus x minus 10y is equal to 0. Oh wait, you know what I did wrong? This is gonna be lambda plus lambda plus 6, lambda plus 3. So this is actually gonna be minus 6 and minus 3. Yeah, I know I'm gonna make this mistake a lot. So this needs to be a minus and this needs to be a minus. So this is going to actually just be x, and then this one is going to be plus 2. So we're going to get, so this becomes, yeah, x minus 2y is equal to 0, and minus x plus 2y is equal to 0. And these are just scalar multiples of each other, right? So that means that we're going to get y is equal to x over 2, or is equal to 1/2 x. So that means if x is 1, then we're going to get 1, 2 is the eigenvector. So this is the vec for lambda 1 equals minus 6. Okay, great. So now we just want to find the other eigenvector. So we're going to get AV is equal to minus 3v. So we're going to get minus 5x minus 2y is equal to minus 3x minus x minus 4y is equal to minus 3y. So then this becomes minus 5x plus y is equal to 0 minus x minus y is equal to 0. Okay, that seems wrong. Oh, wait, because this needs to be minus 2x minus 2y. Okay, and then this is, okay, so then these are scalar multiples. So then we have x minus x equals y. So if x equals 1, then, so then we get 1 minus 1 for lambda 2 equal to minus 3. So then just to plot them, we have 1, 2. Okay, and then this is for lambda negative 6. So they're both negative. So they're all going to, I mean, no matter what, you're decaying exponentially to 0. And then 1 minus 1. Okay, so there we go. So that's the direction field, and everything else is going to go in. But it's not going to, they're not all straight line solutions. Actually, that'd be interesting to see, what does it look like? I mean, is it possible that every initial condition is a straight line solution? I don't know. I don't know if that's possible. Okay, great. So I think there was one other thing. Oh yeah, the general solution is going to be big Y of t is equal to k1 times e to the minus 6t times 1, 2 plus k2 e to the minus 3t times 1 minus 1. All right, so that is problem 3. All right, let's see how many problems are in this section. 25. Maybe let's read through them, see how many of these we want to do. Okay, so for 1 through 10, it's all just spamming, getting comfortable with doing the algebra. Okay, This is going to be a bunch of linear solves. Another linear solve. Okay, this is the exact same problem. Okay, so we have 4. So 1 through 10 is just finding eigenvalues and eigenvectors and potentially finding a general solution. Then we have 11 through 14 is IVP. Okay. Show that A is the only eigenvalue and that every non-zero vector is an eigen. Ooh, that's actually cool. Wait. We're definitely going to do 15. 15 is really good. Absolutely. Okay, 16, upper triangular. Yeah, I want to do 16. 16 seems good. Okay, a matrix of the form is called symmetric. Show that B has real eigenvalues and that if B is non-zero, then A minus lambda times D minus lambda minus B squared. Okay, 17 actually seems pretty good too. All right, see, now we're starting to get to the part that I like because it was too slow of an intro with 3.1, but 3.2 is starting to treat you like an adult. Compute the eigenvalues of a matrix of the form C is equal to where D is 0. Compare your results to the exercise 16. So you're going to get so A minus lambda times 0. So, okay, yeah, we should do 18. Just get really familiar with this stuff. Okay, convert this into first order linear. Compute the characteristic polynomial. Find the eigenvalues. Under what conditions on P and Q are the eigenvalues two distinct real numbers? All right, so 19D seems pretty good. Verify that the eigenvalues are negative if they're real numbers. Interesting. 19D and E seem pretty good. Okay. Another just computation. Plotted solution. Okay, plotted time graphs. Give a behavior. Okay, description. For each second order system, compute eigenvalues. Okay. For each eigenvalue, pick the associated eigenvector v and determine the solution y of t to the system. Compare the results with your calculations. Okay, so I think we're going to just we're sort of going to skip out on these last 5 let's look at 25. Verify that the linear system that models the harmonic oscillator does not have real eigenvalues. Maybe we'll do 25. Okay, so we're going to do one of the IVPs. Okay, we'll do, let's see. Let's do 5, 7. So 5, 7. Then we'll do 11 and 13. Then we'll do 15, 16, 17, 18, and 19. And then 25. All right. Cool. So let's switch over. All right, so problem 5. So we have dx dt is equal to minus x over 2, y dy dt is equal to x minus y over 2. So this is going to be equal to y prime is equal to minus 1/2, 0, 1, minus 1/2 times y. Okay, so now we're going to get so AV is equal to lambda V damn, it's crazy windy right now. Okay, so we just need to do minus 1/2 minus lambda times minus 1/2 minus lambda is equal to 0. So we're going to get 1/4 plus lambda squared is equal to 0. Is that right? How do you factor that? Because you're going to get, 1/2 lambda plus 1/2 lambda. So I don't know if this has any, okay, well, we could always do this. We can always do this. So we have lambda squared plus lambda plus 1/4 is equal to 0. So we can do just our quadratic minus 1 plus or minus the square root of b squared minus 4 times 1/4 times 1 over 2. So this is going to be so if we have, oh yeah, that's true. So minus 1/2. So this is going to go to 0. So then you just have minus 1/2. So is equal to lambda. So we only have one eigenvalue. So then this is going to be, because this is going to be minus 1/4, and that cancels. Wait. Wait, that doesn't check out. Oh yeah, it does. Yeah, it does. Because this becomes 1/4 minus 1/2 plus 1/4. All right, so we're good. So we have our eigen. We have the one. We have the one. So okay, so lambda equals, yes, is minus 1/2. So now what we can do is we can solve for AV is equal to minus 1/2 V. So this turns into minus x over 2 is equal to minus 1/2 x. Okay, then x minus 1/2 y is equal to minus 1/2 y. So then this cancels, and this cancels, and this cancels. So then x is equal to 0, y is free. So the solutions, so the eigenvector is 0, 1. So what we're going to have for our picture is, I don't know about all this, but we're definitely going to have this. So, and then I don't think we're going to be able to find the general solution. Okay, so what else do we need to do? So we're going to have all right. So let's just move on here. this just has no eigenvectors, right? Because oh wait, this is wrong. You're gonna have 3 minus lambda times minus lambda minus 4. So you're gonna get minus 3 lambda plus lambda squared minus 4. So you're gonna get lambda so then evals are lambda 1 equals 4, lambda 2 equals minus 1. Okay, so now we're going to get, so you're going to get minus x plus 4y is equal to 0, and this is going to be 1 minus 4y is equal to 0. So then the solutions are y is equal to 1/4 x. So we have the eigenvector 1, or wait, let's do 4 and 1 for lambda equal to 4. All right. So then the second one is going to be 3x plus 4y is equal to minus x, and x plus 0 is equal to minus y. So then we get 4x plus 4y is equal to 0, and x plus y is equal to 0. So then we get y is equal to minus x. This is going to be 1 minus 1 for lambda equal to minus 1. So now if we draw our picture here, we're going to get 4, 1, 2, 3, 4, 1 here. So we're going to get this like thing like this, and the eigenvalue is positive, so everything goes away from it. And then 1 minus 1 then goes in. Okay, so we have like stuff like this, or like this, or like this, or like this. All right. Problem 11. All right, so we need to solve the IVP. So first off, our system is y prime is equal to minus 2, minus 2, minus 2, 1 times y. So let's just, so we need basically what we're going to do for these initial value problems is we're going to find the eigenvalues and the eigenvectors, and then we're going to use that to solve the general solution. And then with the general solution, we'll be able to find the values. All right, so let's just get into it. So we're going to get minus 2 minus lambda times 1 minus lambda minus 4. So then we're going to get minus 2 plus 2 lambda minus lambda plus lambda squared minus 4. So then we're going to get lambda squared plus lambda minus 6 is equal to 0. So then we can factor this into lambda minus plus 3, lambda plus minus 2 is equal to 0. So then we got lambda 1 equals minus 3, lambda 2 equals 2. Okay, so then we're going to get minus 2x minus 2y is equal to minus 3x. So then we're going to get x minus 2y And then for lambda equal to 2, we're going to get minus 4x minus 2y is equal to 0, and minus 2x. Wait, hold on. This is going to be minus 2x plus y is equal to 2y. Yeah, minus y is equal to 0. Okay, so then since we have two real eigenvalues, our general solution is y of t is equal to k1 times y0 equal to, and then this is going to be for a 1 comma 0. Okay, so what that means really is we're going to get what this turns into is it's going to be like 2k1 plus k2 is equal to 1. K1 minus 2k2 is equal to 0. So we can rewrite this as 2, 1, 1 minus 2 times k1, k2 is equal to 1, 0. Okay. Okay, so how do we solve this? We're going to solve this by 2, 1, 1, 1 minus 2, 0. And we're going to turn this into 2, 1, 1 minus 2, 4, 0. And this would go 0, 5, 1. So then we're going to get 5k2 is equal to 1. So then k2 is equal to 1/5. And then we're just going to have 1 minus 2/5. Or wait. 1 minus 1/5 is equal to 2k1. So k1 equals 2/5. So then our solution is going to be 2, so y of t is equal to 2/5 e to the minus 3t times 2, 1 plus 1/5 e to the 2t. What's up, Hansi? Yeah, nice to see you again, man. What is this going to be? 1 minus 2? Yeah, sometimes I do paper, sometimes I do whiteboard. Just depends on what I'm feeling. All right, let's just do, so B is y0 is equal to 0, 1. So we just need to resolve this equation. 2, 1, 1 minus 2 k1. Okay, so we get So we're still going to get, or aren't we still going to get the same? No, we're not going to get the same thing. So, all right, so 2, 1, 0, 1 minus 2, 1. So we're going to turn this into minus 2, 4, minus 2, 0, 5, minus 2. So then K2 is going to be equal to minus 2 fifths. So then we have 2K1 minus 2 fifths is equal to 0. So then K1 equals 1 fifth. Okay. So then our solution would be y of t is equal to 1 fifth e to the minus 3t to 1 minus 2 fifths e to the 2t 1 minus 2. I think I'm going to check the back of the book just to make sure that we got it right. But I'm pretty sure that is the correct solution. So what section are we on? 3.2. All right, let's go. Okay, so 3.1, 3.2. We're on problem 11. Okay, so A was 1 fifth, 2 fifths. Wait, hold on. Yep, that's correct. I just switched these vectors, but that's fine. And then this is going to be minus 2 fifths and 1 fifth. All right, cool. All right, I don't think we need to do the other one. The other one's, I guess the other one's illustrative because it shows that you only need, yeah, okay. That one's easy because you don't actually have to do the whole linear solve. All right, so our next problem is 13, but I don't know if I want to do 13. 13 is the exact same. All right, maybe 13 we'll just do like this. Okay, so let me just at least write it down the matrix and then we'll do it. So for 13, we have A is equal to minus 4, 1, 2, minus 3, and Y0 is equal to 1, 0, and 2, 1. All right. So we have A is equal to minus 4, 1, 2, minus 3. E is equal to let's just say eigen of A. Okay, so then now that we have the eigenvalues and the vectors, our general solution is, let's just do this at variables, K1, K2. So what we're going to have is, we're going to have so our general solution is going to be K1 times x of minus, or let's just say vals equals oh, it's returned as a matrix. Okay. So we're going to have vals 1 times t times vex. Yes, so this is the general solution, right? Wait, why is it, where's the comma? Oh, no, it's not, it's, okay, yeah, this is correct. I wish it was, I wonder if we could do this. Let's see if we can do this. I really doubt that it's going to give me what I want, but yeah, because square root of 2 is not even rational. But like if I were to do this in like, let's say and then we did eigenvalues of A. Oops. What am I doing? We get oh, we already got that, but for the vectors, Yeah, see how it scaled it not to be unit. I like that it. I prefer when it's not unit, because they scale this so that a squared plus b squared equals 1, but it's just kind of like, why are you doing that? I wonder if actually there's settings to eigen. Is there a way to control that? Yeah, see, I can actually do that. Wait, but it did it anyways. What? That's weird. Okay, it doesn't matter. So this is our general solution, but what we really want is that we're trying to find the system for the so we have y 0 1 is equal to 1 0. Okay, so this is the first initial condition that we're trying to solve. So we're trying to find, I think we're trying to find just like val or x times k1 k2 is equal to, and this is going to be, yeah, y 0 1. So I believe that we can just subtract this, right? But why didn't it? Wait, why didn't it do what I wanted though? Oh, no, it did. It did. So now we need to solve this. This doesn't look right because it's affine. Is that true? No, I don't think that's true. Let me think. No, yeah, we just need to solve that. Oh, but it's so annoying to solve that. So what is this? This is going to be the list 1 0. And then we just want to solve this for k1 and k2. Okay, great. So that's probably the solution. Let's just go check. This is problem 13, right? 2/3 and 1/3? Or wait, was it negative 2/3? No, it wasn't. Did I write it down wrong? -4, 1, 2 minus 3. How could it not be negative? That's super weird to me. All right, let's see what ChatGPT does. Oh, really? I mean, dude, you got to do this. Linear systems are like the bread and butter. They're the only ones that can actually be understood, I feel like. Okay, so we get times this is equal to this. Yeah, okay, wait. How did... Maybe this is not right. Maybe you're not supposed to do this. What equations they get? Is it because the eigenvectors are like... One, 2, and 1 minus 1? I think it's... Wait. I think it is correct. There's no way that this is wrong. I think it's just up to... Because the thing is, the eigenvectors can be scaled and they're still eigenvectors. So what I'm guessing is that... Yeah, that's what I thought. Yeah, eigenvectors are only determined up to a non-zero scalar. So you can just like switch them. Okay. We don't need to keep going on that. Let's see. 15. Okay, so 15 I really wanted to do. Okay, so 15 is going to be easy because show that A is the only eigenvalue and that every non-zero... So the second part is the interesting part. So I want to write it down. So let's say that we have A is equal to A, 0, 0, A. Okay, show A is only eigenval. So the way that we do that is we turn this into A minus lambda, 0, 0, A minus lambda, and we compute the determinant of that. And then we're going to get A minus lambda squared minus 0 is equal to 0. So then the only way to satisfy this is if lambda equals A. So then we're good there. But now we want to show, moving forward, is every non-zero vector is an eigenvector. So that's so cool. So to do this, we need to show that A times V is equal to lambda V for all V. So if we were to just write this as equations, we would get AV is equal to X and Y, right? Because we would get, or it would be AX and AY should be equal to AV. Oh. So it's actually really easy to show it. Just by the definition, just by taking AV, you show that for all V, because this is just the scaling it. Okay, cool. So that was actually a good one and not as hard as I thought it might be. Okay, 16. A matrix of the form is called upper triangular. Suppose, okay, so we have A is equal to A, B, 0, D. Now we want to show, all right, suppose B is non-zero and A is not equal to D. Find eigen of A. Okay. So first off, we're gonna have A minus lambda B 0 D minus lambda. Okay, then we're gonna compute the determinant. It's equal to A minus lambda D minus lambda is equal to 0. So then lambda 1 equals A, lambda 2 equals D. So now if we want to solve for this, we're gonna get AV is equal to lambda V. So first we'd get AV is equal to AV, which is, we're going to have A, B, C, D times V is equal to AX, AY. So then we're going to get AX plus BY is equal to AX. CX plus DY is equal to AY. So then this cancels out and we get BY is equal to 0. And CX plus DY is equal to, or minus AY is equal to 0. So I think Y has to be 0, right? So Y is equal to 0, X is, wait, am I doing this right? This seems wrong. What if we, oh, wait. That's because, no, this is 0. I forgot. This is 0. Yeah. So then we get, so X is free and Y is 0. Okay. This is not there. Okay. So that's for the other, that's okay. Let's do the other one now. Now we have A, B, 0, D times, and we're going to get, V is equal to, this is going to be dx and dy. So then we're going to get ax plus by minus dy is equal to 0, and then we're going to get 0 equals 0. So I don't know. Oh, wait, you know what we're going to do? I know what to do. Okay, so we're going to do ax is equal to b minus, or wait, excuse me, minus b plus d times y. So then we're going to get x is equal to minus b plus d over ay. Or we could also flip it around. We could do y is equal to ax over minus b plus d, something like that. Anyway, so that's these are the two eigen vectors, or these represent the lines. So we could get, well, let's just do it on, what's it called now? So now we can just do this. Or why don't we just do this? A is equal to A, B, 0, D, eigen of A. Bro, it's like, oh, it's just so insane how bad it is. What gives you, is there not something that gives you both? Oh, it gives, okay, there, that's what we want. Yeah, eigensystem. I keep being like, why do we have to call it twice? So we get A and D are the eigenvectors, yep. And then we get 1, 0. Yep, that's what we got. And then finally we get minus b. Oh, wait, minus b. Oh, yeah, I think that's right. Wait, no, I did something wrong. What is it? It's going to be ax plus by is equal to dx. Oh, not dy. Yeah, I factored it wrong. So then it's going to be d minus a times x is equal to by. Okay, all right, cool. So yeah, this is what it is. All right, so now 17. Okay, 17, we have a symmetric matrix. Show that B has real eigenvalues. Well, so we're going to get A minus lambda times D minus lambda minus B squared. So we're going to get AD minus A plus D lambda plus lambda squared. So then we're going to get AD minus B squared. Okay, fuck. Lambda squared minus A plus D in parentheses, lambda, plus AD minus B squared is equal to 0. So show that it has real eigenvalues. Why don't we just do this? Ah, gosh. Oh, wow. Holy cow. And then we need to show that if B is non-zero, they're distinct. That's probably because oh, wait, these are the values. And is that what we're talking about? Yeah, okay. So if B is non-zero is what they said, right? If B is 0, then presumably these like become equal or something, because like I don't know. The question is, B has real eigenvalues only if that quantity under the square root is positive. Oh, but you know what? Wait. That's interesting. I mean, it always comes down to the discriminant when it comes to stuff like that. But I want to know why this thing has to be real. Oh, now that's why. Because both of these terms have to be positive or 0. And then if this is 0, but B is non-zero, then this is going to have 2 values. Okay, that checks out. Even if this is non-zero... Wait, if this is non-zero... Oh, okay, fine, but it's still possible that B is 0, but 2 distinct values, right? That's just in the case that A minus D squared is non-zero. Okay, cool. Yeah. All right, nice. Do we want to do 18? Which ones did I have that we were going to do? I know I said I was going to do 18 and 19. I was going to do 19D and E. So the eigenvalues of this are going to be, I think, 0. Okay, so let's just do 18. 18 is easy. I just have the pro one. Or not the pro one. What is it called? Plus? I think I got plus. I think it's free for students this summer. Yeah, I think it has unlimited prompts. Okay, so we have C is equal to A, B, C, 0. You know what? Let's just do this. Yeah, I've never. Maybe I used DeepSeek like once. Honestly, it's just I'm lazy at this point. I haven't been trying out new AIs. It's not very helpful. All right, I'll skip that one. That one's whatever. This one's yeah. Let's see just a little code golf. Let's see if we can do this. So if we have, actually, I don't really want to do that. That sounds boring. I was thinking of writing the code that turns this into a first order system, but I don't really want to do that. All right, let's just do this one. 19 is not that hard. Let's just do it on paper. All right. All right, so we have y double prime plus p y prime plus q y is equal to 0. So if we turn this into y prime equals v, v prime equals minus p, v minus q y, then this becomes y prime is equal to where y is equal to yv. Then we get 0, 1 minus q minus p. Okay, so then the characteristic polynomial is going to be minus lambda times minus lambda minus p plus q. So we're going to get is equal to 0. So then we're going to get lambda squared plus p lambda plus q is equal to 0. Okay, so then you can do all that, but under what conditions are the so if we had, lambda plus q squared or something like that. Oh wait. Under what conditions on p and q are the eigenvalues two distinct real numbers? So if p, let's see, if we're gonna get, so let's just say this is square root of q. Then we're gonna get lambda squared plus 2 root q lambda plus q. So if p was equal to 2 root q, then we would only have one real eigenvalue. Okay, and I don't know how to verify that the eigenvalues are negative if they're real numbers. Let's see, what was 25 again? I might skip this one. I'm probably going to end it right now. And then we're going to jump on to, I think I might eat something. And then we're going to do 3.3 potentially. And then I got to do a bunch of linear algebra from other class. So E, if they're real, oh wait. Oh yeah, no, I did this wrong. Okay. So there are two distinct solutions so we have minus p plus or minus the square root of p squared minus 4q. So if p squared minus 4q is greater than 0, then two solutions. But if p, okay, wait, if we just did p squared is equal to 4q. Yeah. So I did a simple case of like just this, but this is more general. Because this is strictly greater than 0. Okay, so that covers more cases. All right. All right, so that is section 3.2. We'll hop back into 3.3 and do Phase portraits for linear systems with real eigenvalues. I think that this one might be fun. It's going to be drawing a lot of pictures, I think. Kind of excited for 3.4, really. All right, so we'll do... Oh, this is cool. I like this. Yeah, I read this yesterday. All right, it's going to be a bunch of sketching. Okay, this might go by fast, actually, if that's the case. It's just sketching. All right, so this one, like 19, determine the type of... You basically you find the eigenvalues, and if any of if they're all negative, then it's a stable, whatever it's called, a sink. It's a saddle if there's one that's not and one that is, and then it's a source if they're both positive. All right, then for calculate all straight line solutions, you just find the eigenvectors. Okay, this is more of the same. Oh, they really hammer this stuff. Okay, this one might be cool. Small pond of fish. Okay, I really want to get to 3.4. All right, I'm going to go make some food.